So, good afternoon to this second section of Tema. We will start with the paper, which is Compact and Fast Indexes for Translation-Related Tasks. This is from Jorge Costa, Luís Gomes, Gabriel Lopes, Luís Russo, and Nieves Barbosa. So, 25 minutes and 5 minutes to questions.
Thank you. Good afternoon, everyone. I'm here to present a work based on using and studying compact or compressed text indexes and fast for translation-related tasks. Well, translating a text is a difficult task because choosing the best translation for each word or multi-word and binding them is not easy. So human translators who have this difficult task in hands can use machine translation tools to help in this translation process. One of these machine translation tools is the bilingual concordancer, which is the test case for this paper, which is a tool that supports the post-editing of machine-made translations. That means that the machine makes or can provide some possible translation pairs, and then the translator has the job of choosing the correct ones and the incorrect ones. So how does this tool helps in this process? So here on the left we have a fragment of two texts, one in English and one in Portuguese, and each one is the translation of each other. And we have 14 different segments that are aligned. So for the bilingual concordancer, we can give a query, like for instance, European in English and Europeia in Portuguese. And then the concordancer will return the occurrences that happened in the same aligned segment. For instance, European Union and União Europeia in Portuguese, both occurrences of European and Europeia occur in the same aligned segment. This is what we call a co-occurrence. When this happens, when we have two co-occurrences or one co-occurrence in aligned segments, and this happens several times along the text, the probability of this pair being a correct translation, is higher. So only this result is helpful for the translators. Alongside this, we provide the user the opportunity of showing some context. It's the context window over there, which we put for the example 3. In which we show the 3 segments of the alignment before the occurrence and the 3 segments next to the occurrence, except in the cases where the text stops, like in the second co-occurrence, there's nothing more after, so we don't put nothing. So by having this information of the co-occurrences and the context, this makes it a lot easier for the translators to choose the correct translation, especially when we have the cases where we have many doubts. So, but what is the problem here? Well, well-known concordancers like the TransSearch, like the Sketch Engine, use a fixed grain alignment. What does this mean? The alignment can be of several different coarseness. You can have segments like the one that I showed you before, small segments with less tokens, like 5 tokens at most. This is what we call a fine alignment. And we can have as well coarser alignments like whole paragraphs, whole sentences aligned with each other. So if you give to the user a chance of choosing this coarseness, like you can look at the paragraphs or you can look at more specific the words and multi-words, this gives him the more flexibility on each, depending on the case that he's studying. Alongside this, it's difficult to find an efficient space-time trade-off for such an application, because you can have lots of texts in memory, because it's faster if they are in memory. And typically the text indexes with fast search query capacity demands lots of space in memory. So our proposal is to build a framework using two different layers. The first one is what we call the compression layer, because it uses two compressed text indexes for managing the text. So one for one language, for the text in one language, and another one for the text in the other language. And the main job of this layer is to return the offsets of the occurrences of an expression. I mean, I find for European, and the text index gives me where it occurs in the text, all of the occurrences. And using these text indexes gives us a memory consumption of 25 to 40% of the text size. So a lot less than the size of the actual text. And it gives us the query response time in linear time. But so far we only have the offsets of the occurrences in one language and in another language. We need to bind them. So we have another layer, an alignment layer of uncompressed structures that any of you will know, as I will show you later, for representing the alignment like the one I showed you before. And this here, by using the offsets from the previous layer, can return the alignment segments where these expressions in the query occurs. So I will start first with the compression layer, and we have two different alternatives. First, we use a byte-oriented coded wavelet tree. So I'll just give you a brief explanation. We have every token in the text that is separated by a blank space. We replace it by code words. We have the example there, to be or not to be, that is the question. And the information on the right, we have all the words separated. And we give them a different code. Each B1, B2, B3, B4 represents a byte. The tokens that are more frequent, we give them smaller code words to occupy less space. If we have two that occurs millions of times in a text, we give them smaller code words to have a better memory consumption. And then we distribute all the code words by the several levels of the tree. For instance, I have there the word question with 3 bytes in the code word, B4, B5, and B2. And if you look to the right in the picture, you have the first byte B4 in the root level, right on the right. And so the first level has all the first bytes of every code word. Then in the second level, we have question over there on the right as well with B5. B5 is the second byte. Every second level, the whole second level has all the second bytes. And the same for the third byte, B2, the only one here, which the third level will always have all the third bytes, and so on and so on. And this structure gives us what we want. It can count the occurrences of an expression, and especially it can locate the occurrences in the text. And with the tree topology, we have a very good query time performance, as I'm going to show you in the results later. But we tested this with an alternative. The alternative is the word-based compressed suffix array. So we have the source text there. I give you a shorter example, to be or not to be only. And we replace every token by an ID, an integer ID, like B is replaced by 1, not is replaced by 2, and so on. And then we have this SID here, which replaces the tokens for the ID. For instance, 2 is replaced by 4, B is replaced by 1, and so on. So here we have a small kind of compression. So we took away all the tokens and replaced by integers. But alongside this, we put all the integers in a suffix array, which is compressed. And then we discard the sequence. And this structure also supports the count and locate operations, which is what we want. So these are the two alternatives for representing the texts, and now we have to represent the alignment. I remember you the example that I showed you before, but if you remember, I told you that we want to have different kind of coarseness. This is only a fine alignment, only with small segments of 3, 4, 5 tokens, or 1. So for example purpose, I will divide this alignment in 3. And I consider these 3 divisions by a coarse segment, so a bigger segment. And now, considering these 14 segments of the fine alignment and the 3 from the coarse, I'll show you how we can represent them. First, the first approach is by using bitmaps. So, we have 3 different bitmaps, 2 for representing the fine alignment, the one in English and the one in Portuguese, and 1 for representing the coarse. So, the idea is pretty simple. Every one represents a new segment, the beginning of a new segment. So, if we look to the Portuguese side, we have A, the first token. So, we put a 1 and 1 0. So, we have only 1 0 as every 0 represents a single token. Then we move to the second segment, another 1, because it starts a new segment, and then 2 zeros, because we have Republika Slovakia, in 2 different tokens. And we repeat that for every segment of the alignment. But this only represents the fine one. For the coarser, it's easier, because you only need 1. Why? This happens in every case. Every time the coarse alignment is the same in one side and the other. So if we look at here, this is an accurate case where we have the first coarse segment has 4 segments on English side and 4 on the Portuguese. The second one has 6 on the English and 6 in Portuguese. And this happens all the time. So we only need 1 bitmap for the coarse, for representing the coarse alignment. So the same idea, the first segment starts with a 1, and then each 0 in this case represents a fine segment. In English and in Portuguese we have 4, so we put 4 zeros. The next segment, another 1, 6 zeros for the 6 different segments. And this is always treated the same way. But how do we search for anything here? We use the rank and select queries. The rank queries count the number of 1s or 0s in 1 bitmap until a position. The position marked with the red arrow there is the position 10. So we want to count the number of 1s until the position 10. If you look at the picture, there are 2. The same thing for the zeros. Count the number of zeros until the position 10, and we have 9. The position starts at 0. The first position is 0. Select is a little bit different because instead of counting, we want to find the occurrence of the second one in this particular example here on the left. So we find that the second one, it's at position 5, and we can do the same for finding the second 0, for instance, which is in position 2. So by using a combination of these 2 operations, we can achieve the results that we want, which is to find if the offsets are in aligned segments. But as in the compression layer, here we also have a different alternative. This one uses arrays of integers, the most completely simple, where we have 5 different arrays in this case. We have 2 for the fine segments, 2 for the coarse, and 1 that relates the 2. So here, instead of having 1s and 0s, we represent in each position the starting offset of the segment. The same example I showed you before. In Portuguese, we have the first segment, which starts at position 0. It's this array here. And then the next one starts at position 1, But the third one starts at position 3 because the second has 2 different tokens. So A is 0, Republic is 1, Slovakia is 2, and then the third segment starts at the third offset. And this, so on, through the whole alignment. The same thing happens for the core segments. Here we have, in Portuguese as well, the one on the right there. The first one starts at 0. The second starts at the offset 10, which is the 5th segment there, AS, and so on. Here we have 2 different arrays because despite the core segment have the same number of fine segments on the left and on the right, the starting offsets can be different. For instance, on the left we have 4 tokens, and on the right we have 10. So we need to account for that, so we need to have 2 different arrays. The 5th one is implicit, is represented here by these bigger bars. The only thing that this array does is to filter the search. So it shows us in the fine arrays where the coarse segment starts. And we look for the correct segments using the binary search algorithm. That's why I call it there arrays plus bisection. So these are the 2 alternatives. For experimental results, we used 4 different corpora. One very, very small with 1.6 megabytes, which is with the European treaties. The next one a little bit bigger, it has information about medication and stuff like that. Then Europarl, which has the transcriptions of the conversations in the Parliament, European Parliament. And then DGT, which has translation memories as well associated with the European Parliament. And we measured the memory consumption using megabytes and the total query time in seconds. And we used 700,000 different queries from different corpora, like extracted from these different 4 corpora randomly. And if we look especially at the space used percentage, if we look at any alternative, because we combined the 4, every alternative takes less than the text size. So we can have this framework occupying less space than the text size. The word-based compressed suffix array, which are the 2 on the right, is the most compressed one, while the bitmaps are the most compressed solution from the alignment layer. Why? Well, especially because the bitmaps, every position has 1 bit only in space, and it has only 3, while the other solution needs 5 arrays. While in the structures, the compressed structures, this happens because the tree has a tree topology which always takes more space. Comparing the texts, EUCONST, the first one, has a higher space use percentage because it's a smaller one, has less repetition, so we cannot compress it as much as on the rest. In terms of time, we have on the right the total time for the tree and the suffix array, and we needed only to test the suffix array for the first ones because the time spent is much bigger. So the difference is so high that we don't think that it's a good solution for representing this framework. Comparing the arrays with the bitmaps, well, the arrays are faster, and it leaves to the user to choose if he wants more space or more speed. Again, here on the right, we have the average time in microseconds, and you can see that for each query, it only takes at most 18 microseconds to answer. Again, the first one with higher numbers because of the less repetition. In terms of future work, this compressed framework is really generic and can be used for any different machine translation tasks, like supporting lexica, determination of language models, used to mine new translations. And one of the particular examples for mining new translations is to use variables within the expressions, like here, where I put a V in the middle of has and provided, And this V can be replaced by anything, like as already provided or as just provided, and so on, the things that you can remember. And this can work as a fishnet to find new and correct translations, to increase the base knowledge of the framework, and to give to the translator more different translations to work with. And that's my presentation. Thank you.
Questions, please? No questions? Thank you. We may start with the second paper. It is called Defining a Probabilistic Translation Dictionaries, Álgebra. Alberto Simões, José João Almeida, and Nuno Ramos Carvalho.
Capta o som.
Capta o som que eu estou a falar? Não. Então eu vou tentar. My name is the first one, and we are going to speak about probabilistic translation dictionaries. The first thing is, what is a probabilistic translation dictionary? As in previous presentation, we see that there are several tools that can, starting from parallel corpora, from the text and its translation, somehow magically, statistically guess alignment, correspondence between words. If we try to organize that by word, we can in fact establish some sort of a correspondence between a word and the set of its possible translations, and in fact the set of translation and its accuracy. If we collect that probabilistic dictionary, we end up with things like this. Europe has occurred that many times and has some popular translation with some sort of probability. It's not a real probability, but somehow has most common translations which somehow are stronger cues. In this presentation, Before that, normally these probabilistic translation dictionaries, these PTDs, come from parallel corpora, from text and its translation, but we don't really care where they come from. In this presentation, we want to discuss if we have them, what can we do with that, how they can contribute to our happiness and so on. So, from the creation process, we get two probabilistic translation dictionaries, from language 1 to language target, and from language target to language source. So, the structure can be a metadata and a dictionary. Metadata has the usual stuff that metadata always have, we won't discuss it. And the dictionary has a correspondence between a word and his info. His info has at least the number of occurrences and the translation and its probability. In the end, that can be used in many different ways, in search engines, in trying associate each word and its translation to a button that looks it in the corpus. We can do it more inserted in a search engine or other different things. This is from a real page we can find in the net. The main message is that, okay, PTDs are wonderful, good, rich, whatever, but we need to discuss it and to standardize it somehow. We need to define clearly and formally its algebra, its functions. I mean, the set of constructors that build PTDs from whatever we can use to build them. A set of functions that transform, associate, compose, and so on, PTDs. A set of publishers that produce other useful things from PTDs. Of course, an interchange format and some formalization would be welcome, and this is the main message of this talk. Menu, we don't care about menus. PTD algebra, this is a little bit crowded slide, sorry. If I have a PTD, several things are expected. The domain of a PTD would be the set of words that are in the PTD, that are in the dictionary. And the range, the set of words that are translations. If we apply a word with a PTD, we expect to have an entry that, as shown before, has the table of translations of that word and the number of occurrences. Union, intersection, composition, domain restriction, and domain subtraction are common functions when we have mappings, and that apply with some adaptations here. Filter mappings are also things that are very used in those kind of objects. In the end, we also have some extractors that are very popular. For instance, extract B-word sets. For instance, strong relations between a word and its translation. If we have many of them, they are very useful to alignment processes, or even unambiguous concept translation sets, we'll skip it for now. The union. Everyone knows what is the union of sets, even the union of mappings. But in this case, the union is slightly different because, in fact, as the words in different corpora may have different occurrences, when we join them together, when we make the union, we have to get to set different ways for the different sizes. We will speak a little bit about this. This operation is very important because, in fact, it can be used to join together things that came from very different corpora in order to obtain a universal PTD that is useful for several tasks, and even to deal with scalability. I mean, if we have a huge corpora, as some of the corpora referred in previous presentation, sometimes it's difficult to apply the extraction process, and if we divide it in several slices, we can, in the end, make the union of all of them. So the scalability depends on the union process in some situations, at least in some algorithms. For instance, if we take two correspondence of doente, when we join them together, we see that the influence of the big corpus is much higher than the influence of the small corpus. Nevertheless, the small corpus introduced some new meanings that were not in the other, but with very small probability because the number of occurrences was very small. But so this is some sort of fuzzy set union, but the details of how we calculate it are not so trivial as I was expecting, because in natural language we often see more relations than difference. I mean, if a thing happens 2 times more, it's very different if it has 10 more occurrences. So we have to work logarithmic in some situations, but the main intuition is try to make the fuzzy set union, but taking care of the logarithmic scale. The intersection can be used to extract what is common between different things. It's useful to find or to reject things that are sporadic, that occurred once but are not relevant. It can be used to extract noise, to remove noise. The intersection chooses the smallest. It follows the traditional multi-set intersection. Domain restriction is useful, for instance, to select, to reduce the size of a probabilistic translation dictionary to an active domain, and domain subtraction to remove some things that we have good reasons to remove. The totalization, after several operations, the sum of the probabilities is not 100, and sometimes we want to totalize means to scale it in order to be 100. The composition is more interesting. If we have two different dictionaries, we can compose it, for instance, Portuguese-English and then English-French. The composition will build a dictionary from Portuguese to French. It has several situations. For instance, affluenza, I think it's in Galician. The correspondence of the second row is in English, and the third row is in Italian. If we calculate the composition, affluenza, flow, inundazioni, makes affluenza inundazioni with a probability of the product of the probabilities. I mean, it returns this. Some of the correspondence are noisy or wrong, especially the most, the less probable, with the numbers very small. But this triangulation process is very useful, for instance, for minority languages, and we can even make the composition with the inverse dictionary. I mean, casa, once more, casa is in Galician, not in Portuguese. Casa to English and English to Galician again. If we make the composition, we get Galician to Galician. I mean, we get some sort of what we call not a scene set, not a set of synonyms, but a probabilistic scene set. We call this PSS. These probabilistic scene sets have been used to several tasks, and it's amazing what we can do with this, even being so noisy. For instance, we can calculate which word is more similar with another. For instance, in program comprehension, we are using this to try to see what is the piece of code that is nearer from a keyword. This is also useful for things like building dictionaries or as a starting point, not as a final point, of course. Filtering, as you may guess, it's according to some property, remove things that are not necessary or not useful. For instance, in this situation, remove things that have a probability smaller than a given value. PTDs can also be used in, have been used in terminology extraction. I mean, we build some sort of a pattern that say something that corresponds to an English construction with the opposite order correspond to something that we can extract. This depends on having the correspondence between the sub-elements. Of course, for the end users, we can also build some prettier thing with examples. This is very popular in the translation community at our university. A small case study from some documentation about a source. We built in spending near 1 day of work. We built a corpus, a parallel corpus. We get 2 different PDF guides from things like algar do carvão and things like that in Portuguese and English. We extract some information about the site of SATA and from TAP the review. Language Portuguese and English, and the first thing was to make the parallel corpora, to make the translation memory in the translation memory exchange format, and that is our start point. After that, we did no verification at all, so the thing is very noisy. Several parts of the SATA site are not translated. Some are wrong in the translation, or some have very creative translations. So don't expect miracles about this. But using our toolkit, which is in fact an implementation of the calculator we present before, we have done, we can do several things. I will try not to make the demo, but we can query English-Portuguese, we can query Portuguese-English, we can compose Portuguese, English-Portuguese with Portuguese-English, calculating a probabilistic thin set for English or for Portuguese. Lowercase, normalize all of this, and this is the kind of answer we obtained directly. This is a cutted screenshot with no changes at all. For instance, Miradouro returns viewpoint, view, viewpoints, lookout, points, dragon, cafe. So we can see that normally the first ones are useful. Normally the last ones are garbage, noise, unuseful things. But Miradouros appears, Belvederes appears things that are not present in the singular. But even for study a language, this is normally useful. This is the result of querying the probabilistic scene set resulting from the composition of the two of them. The composition of these two took perhaps 20 seconds to calculate. I will not do it here, but things like this is the result we obtain. Miradouro, Belvedere, Vista, Mirante, Arif, Ponto, Café again. Once more, the last ones are not useful, but we can even filter from a given point or see it by hand. It has many more, but with the probability very, very, very low, paisagem, the same thing. It was a surprise for me to see things like cenário paisagístico, terreno, campo. Some of them are useful, really useful. Of course, some of the lower ones are garbage again. In the English side, a similar thing: trip, journey, travel, the return, no. Flight, stroll. Most of the expected synonyms are present clearly in the first occurrences. Landscape, a similar thing. But that is not so successful when we deal with other classes of information. For instance, verbs between Portuguese and English are complex because the number of occurrences is quite different. For instance, a verb in English may have 3 or 4 forms, and in Portuguese it's easy to have 100 times more than that. This makes the correspondence in one of the directions very weak. And so the next case study, experience, demo, whatever you want, was make a literature corpus. We get books these times, 8 books, wonderful books, which were Harry Potter and the Sorcerer something, Código da Vinci, Aos Prestes Zarathustra from Nietzsche, some Poirot, I don't remember, really miscellaneous things. And even some of the things are in Brazilian Portuguese and some in European Portuguese. So it was a very quick hacking, asking for the help of my students. So it is not the ideal situation. We get underline it. Then we build a annotated TMX, which is in fact tag all the words in Portuguese and in English. Then we establish a simplification function that make the text again, but substituting some words by the lemma, by the radical if you want, especially the verbs and adjectives that have a different flexion. The others, we keep it the same. We build the PTD, and we did a mapping of remove everything except the verbs in order to study just the verbs. And after that, and we also lowercase all the things. And the query, the composition to make the PSS produce something like this. When the PSS applied to a verb like say in English, say, tell, ask, answer, reply, be the auxiliary verbs appeared as noise in almost the queries. I should also, in the filter stuff, remove the be and in the get and 2 or more auxiliary verbs in order to concentrate. Explain, speak, demand, explain, exclaim, respond, constitute, keep, cry, wonder. The first slide of this appeared to have relation with say that was much better than what I was expecting. Believe, think, trust, suspect, buy, perhaps. Assume, swear, be, go, auxiliaries again, will, auxiliaries. But that is not so, that does not work so well when we have verbs that appear just 1 time or 2 times in the corpus, in which the noise is much bigger. But what is the main conclusion, the main thing I want to discuss with you? PTDs sometimes are noisy things, but if we can filter, extract, choose the useful stuff in it, if we have a number that shows the confidence we have, that make it possible to sort in order to have a better ranking in the first places, we obtain things that I believe that can be used in several tasks, either in the humanities or as helping query, annotating looking for similarity between words or proximity between words. And I believe that this really can be useful, especially if we can define some sort of interchange format, some sort of algebra, a calculator, a set of implementations that accept this kind of resources. And there are already several projects. One of them appears the Perfide project that makes it possible to download PTDs, big PTDs, from corpora, from real size like the Europarl, the Eurolex, and several other, and from several types. But this was the things I have to show you. Sorry if I exceed the time.
We are on time. We are using some time from the previous session. So, thank you. Questions?
Please, can you explain a little bit how do you compute the calculations of the composition operators, the probabilities? Because I think it was not well, or it was not presented.
No.
The composition or even the union, how do you compute the values?
Each one has a different trick. For instance, the composition. When we have a first arrow with 35 and a second arrow with 62, we multiply the two of them and obtain 18.
Okay.
Casa also appeared in the first, the second, and so we add all of them, and we normalize it. I think we divide it by 2, I'm not sure. But it's in fact the multiplication of the row and had the common words.
Okay.
The number of occurrences kept, and there are 2 or 3 special situations we also have to deal with it. We have some hesitations about some of the definitions that should be done, should be useful, and we are still tuning. And any suggestions you might do would be very, very welcome. And in some situations, it happens that the total, in almost all the situations, the sum of the things is not 100, which sometimes makes sense, sometimes doesn't. In fact, these are not really probabilities. These are some sort of confidence measures.
Kind of strength of the translation. So, are there other groups in the world working in this subject of probabilistic dictionary translation? And if so, are you trying to normalize these operators? Because I think that what you were saying was that it is important to make a kind of normalization of these operators in order to the community to use them.
That's exactly why we wrote this article. Okay. Try to discuss it, try to make a proposition, try to start with that. We have speak about these subjects with Tideman from Opus project, but we have seen several groups that are producing information, GISA++, tool, several of you have some specific aligner that can produce things like this, even if it is not exporting that as a final result. But if in this case we have made a proposition and a toolkit, a toolkit in Perl that is calculating this. Yes. We are using that massively in our project of Perfide, which has some dozens of corpora, some of them very big, and dealing with that Russian, English, and several situations with which makes some surprises from time to time. Russian is very good because I don't speak Russian and I always believe that everything is perfect. But nevertheless, what we would like is, as you say, to try to have a common language to speak, as we like the calculators in mathematics, to say the union. And it's wonderful to be able to have a common knowledge and say intersection, and everyone knows what we are speaking. I would like that to be also possible in PTDs.
Okay, I hope so, and thank you.
I have a question and a comment. I would say that if the sum is higher than 100%, there's something wrong. But, well, I have a question. How do you compare your work with other approaches? I didn't get out to your explanation about that.
In fact, we see many work in producing information like this, but I have not seen propositions, discussions of algebra of PTDs. I tried to contact some investigators in order to make a common effort to do that. But one of the things that is somehow problematic is that it's very easy to have a different PTD, and if we could have a common PTD, it would be much easier to share resources. But unfortunately, I saw similar work in the fuzzy sets, multi-sets, but this thing have some, has a few details that change from a traditional fuzzy set or multi-set because of the number of number of occurrences that make things being to be adapted from that. But I also would be very happy if you could suggest me some articles to read, because I'm sure there are other similar approaches.
Thank you. More questions? Thank you. Well, next and last paper for this afternoon is Towards the Automatic Enrichment of a Portuguese Word Net and with Dictionary Definitions, Hugo Gonçalo Oliveira and Paulo Gomes.
carregar naquele botão ali, embaixo.
Sim.
Pois é, não vejo o rato também. Ok. Não sei, depois eu coloco aqui.
So, good afternoon. I will talk about the automatic enrichment of Portuguese WordNet with dictionary definitions. The presentation will start with an introduction, I would say quite long introduction, because I will talk about WordNets with a special focus on Portuguese WordNets, then about the importance of glosses in WordNets. Then I'll present a procedure, a generic procedure for assigning definitions to the syntax of a WordNet. I'll talk about some details in order to do this for Portuguese, to Portuguese WordNet, and then I'll show some results and some evaluation and some concluding remarks. As you may know, and this is not working, I don't know why. As you may know, WordNets are broad coverage lexical knowledge bases, which are very useful in a broad range of natural language processing tasks. They have been used in question answering, word sensitive evaluation, and so on. And they are structured on words and meanings. More specifically, they are structured on synsets, which are groups of synonymous words. You can see, if you think of a WordNet as an ontology, you can see these synsets as the concepts of an ontology. Usually, these synsets have glosses, which are natural language descriptions of the meaning of the context, of the synset, I mean. As in a dictionary, you have definitions. And you have semantic relations which connect the synsets according to their meanings and help to understand the interactions between the words of a language. The first WordNet was Princeton WordNet. Now there are WordNets in many, many languages, but the first one was made for English. However, this is a resource, and most WordNets are created manually, which involves much human effort, and people have to deal with time issues and also with information sparsity, which means they have to spend a lot of time, and they will never get a complete WordNet because language is always evolving and so on. So there are approaches to the automatic construction of WordNets, or first to the automatic enrichment of WordNets after exploiting other sources of knowledge, and also approaches on the automatic creation of WordNets. Most of these approaches are based on the translation of an existing WordNet, usually Princeton WordNet, to a target language. In my opinion, this is not the right way to do this, because different languages cover different realities, and it's not straightforward to find a mapping between the words of a language and the words of another language. So there are other approaches, the minority of approaches. One of them is my work in the last years, where we try to create a WordNet by exploiting existing lexical resources for a language, and specifically for that language. This slide is about the Portuguese WordNets. It is commonly said that there is not a Portuguese WordNet, but actually there are at least 5. But they all have, I would say, strong limitations, including OnTop-PT, which is the project I've been working on. But starting with the WordNet PT, the main problem about this WordNet, which is probably the first Portuguese WordNet, is that you cannot download it. So you can query it online, you can use it online, but just in a web interface. And its creation is manual. Then there are 3 Portuguese WordNets, 2 of them for targeting the Brazilian Portuguese, and 1 targeting the European Portuguese, which are, all the 3 are based on the translation of part of the Princeton WordNet. The first one, WordNet BR, it contains synsets that were created manually for Portuguese, and they are actually available. And then the relations are inherited from Princeton WordNet after some matches between the synsets. And the relations are not available. There is multi-WordNet, which you can use if you pay a license. It's based on the translation of key synsets in Princeton WordNet, and also relations inherited. And this resource only covers nouns. The others cover other words, other categories of words. There is a very recent initiative, which is OpenWordNet PT, which is freely available, and the construction is more or less the same as multi-WordNet. And then there is OnTop-PT, which is the project I've been working on. It's a free WordNet for Portuguese created automatically. of course, this is not a resource as reliable as the others, but as you see from the numbers that should be, okay? As you see from these numbers, this is a much larger resource, both in terms of lexical items, scene sets, relations, and also kinds of relations. It's the only one with a size comparable to Princeton WordNet. If you look at the glosses, you see that the WordNet PT contains glosses. They seem quite good if you search on the web. But the other three resources do not contain glosses. At least they do not contain glosses in Portuguese. You can always translate them. You can always inherit the glosses from the English WordNet and then translate them, but they are not written in Portuguese. And since the last version of OntoPT, you have glosses in the scene sets, which were assigned to the scene sets by the approach I will talk about in a few moments. But of course, as I said, it's not a 100% reliable approach as the others are virtually, because they were created manually. The importance of glosses. So, glosses are important because they add specific information to the scene sets, specific information that sometimes does not fit in the covered semantic relations, and information that is important to understand the meaning of the scene set. Moreover, they enable to use the WordNet as a dictionary, and they are additional sources of context which can be, which can be used in tasks such as word sense disambiguation. So the goal of this work, okay, and their creation tends not to be a priority, as you've seen, for instance, in the previous examples. The WordNets, Portuguese WordNets that derive from the translation of Princeton WordNet do not have glosses written in Portuguese. So our goal is to enrich OntoPT with dictionary definitions. It was, now it has the definitions. But we wanted, from the beginning, we wanted to keep the construction of OntoPT fully automatic. So we decided for an automatic approach for this task. This work has some similarities with some work that was made for German, for the GermanNet, where some dictionary definitions were mapped, were aligned with the GermanNet scene sets. GermanNet is created manually, but in the last years, the authors are exploring some automatic approaches for enriching the resource. So, in order to assign the definitions, which can be seen as glosses, to the scene sets of WordNet, we must have a WordNet, which can be seen as a graph with scene sets as nodes and relations as the edges. We should know that the scene set groups different word senses, groups word senses, and these word senses are represented by words. And a dictionary, I think everybody knows what a dictionary is. It's mapping between words and definitions, and each definition describes the meaning, a sense of the keyword. And the procedure is as simple as this. So we first need to set the context of the scene set, which will contain all the words in the scene set and in the related scene sets. Then we must retrieve all the candidate definitions for this scene set, which will basically be all the definitions of one of the words in the scene set. Then we need to set the context of the definition, which will contain all the lemmas, the content lemmas in the definition. And then we score the candidate definitions according to the intersection between the definition context and the scene set context. We select the best definition with the highest score. And we should have some threshold to make sure that we do not select a definition with very low intersection. So, for Portuguese, we have used, as I said earlier, we have used OntoPT as our WordNet. We have used two Portuguese dictionaries, which are open. And we have used, we also made some experiments with Wikipedia, because as you know, the first sentence of Wikipedia can usually be used and has been used as definition for the article. We have also used part of speech tagger, where we use the available models for Portuguese of OpenNLP and also a lemmatizer with rules based on the OpenNLP tags. And now just a brief overview on the creation of OntoPT in order to once again introduce our goal. So OntoPT is created by a framework that I've called ECHO. It's an automatic approach with 3 automatic steps. It starts with extracting semantic relations from text. It analyzes the text and it extracts relations established between words. In the second step, it analyzes the synonymy relations extracted in order to discover synsets. If possible, we use already existing synsets in available resources, such as the Open WordNet PT and the WordNet BR, which I talked about before. Then, in the third step, the goal is to assign each word argument in a relation to a suitable synset. And the goal of this work is to add a fourth automatic step to ECHO, which will assign glosses, assign dictionary definitions to the synsets. Also, in order to perform this work, we needed to convert the dictionaries to a very simple plain text format. We have some additional processing to different dictionaries. For instance, for Dicionário Aberto, we made some automatic replacements toward the modernization because Dicionário Aberto is a dictionary with about 100 years old, and some words have changed. We have used a parser we have developed some years ago for processing Wiktionary and for transforming its contents, which are in Wikitext, into a plain text format. And for Wikipedia, the processing was very simple. We basically extracted all the abstracts that match the typical definition pattern as this one. And then we discarded some definitions that would not be informative enough for the synsets. For instance, definitions with enumerations, which are usually enumerations of synonyms, and the synset should already contain these synonyms. We also discarded synonym definitions, such as this one, and also definitions of words that were not closed category words, and also definitions of verbs which were not in the infinitive, which sometimes occur in Wiktionary. And these are the sizes of the dictionaries we obtained. So using Dicionário Aberto, we obtain, so the largest dictionary, you can call it like that, was extracted from Wikipedia, then Dicionário Aberto, and then Wiktionary PT. As expected, Wiktionary is a much smaller resource, so it has also less definition and also less definitions. Then we merge Dicionário Aberto in Dictionary PT in order to have a larger dictionary, and then we merge all the 3. As for the scoring, we based the score on the intersection between context, but we boosted those definitions that referred an hypernym of the synset. Though that H is the set of hypernyms of the synset. The reason for doing this is because for nouns, most definitions start or use the hypernym. Usually, the noun is defined in terms of its hypernym, and then some specific properties are given in order to distinguish this instance of the hypernym and the other instances. This is one example of such a definition. And we set the acceptance threshold to 1, which meant that we only accepted definitions which had either 2 related words to the synset or 1 hypernym. And here are 2 examples just to make this procedure more clear. So we have that synset, alugar, arrendar, locar, alquilar. And we have a relevant relation, alugar, arrendamento. Well, it's a synset that is caused by the first synset, alugar, arrendamento, and so on. And we have 4 candidate definitions. The first one is the selected because it contains 2 words which are caused by the first synset. Sorry, which are causes of the first synset. The second example, which is slightly more complex, we have one synset, once again, with 4 words. We have 4 relevant relations and 4 candidate definitions. We select the first 2 because the first one contains 1 word that is an hypernym of the synset and 2 words that are a cause of the synset. And then we have another definition with 2 words that are hypernyms of the scene set. So we select these 2. The results we obtain after using these different resources, these different dictionaries, shown that the dictionary from where we could cover more scene sets was Dicionário Aberto, with about 29% of the scene sets with the definition. Wikipedia, although being the largest resource, is the resource that leads to less coverage. This is easily explained by the fact that Wikipedia contains a lot of knowledge that is commonly not present in dictionaries. So it contains a lot of information on world knowledge, on facts, some of them very recent facts, named entities, and so on. And then we merged Dicionário Aberto and Wiktionary PT. We increased the scene set coverage, and when we add Wikipedia, the coverage is just slightly increased. In order to evaluate this work, we had 2 human judges that classified random pairs of scene sets and definitions. We decided to use only those definitions from Dicionário Aberto and Wiktionary PT, and we have excluding scene sets of size 1. And each judge had to classify the pair, the scene set definition pair, into one of the following. If the definition was not valid for any word of the scene sets, it will be classified, the pair will be classified as 0. If it was valid for 1 word, it will be classified as 1. 2, if it was valid for 2 words, and 3, if it was valid for more than 2 words. And the results are here, or should be. As expected, none of the pairs had a definition that was not valid for any word of the scene set. This makes sense because all the candidate definitions were already a definition of one of the words in the scene set. On the other, opposite, about 79 to 80% of the pairs had definitions valid for 3 or more words in the scene set. And I see this value as an approximation to the accuracy of this procedure because it's not common. I can see any situation where you have 2 completely different scene sets that share 3 words but have completely different meanings. So I would say that this procedure is about 80% accurate. So to conclude, this was just a first approach to assign glosses to a word net by automatic means. This was more or less the description of what we have done to achieve this goal. Now, in the last version of OnTopET, which was released about 2 weeks ago, you have glosses in the scene sets. The accuracy is more or less the same, so it's still far from perfect. It's 80%, but it's okay for many situations. Now we have more scene sets, and 40% of those scene sets have a definition. The main reasons for this increase is that now we have a larger OnTopET. We have used the more recent version of Wiktionary, and we have used OpenWordNet, which was not being used before. So we have more context, and it's easier to find definitions. And we also now, when setting the context of a scene set, sometimes we have multi-word expressions, and in the work that I presented, we did not split the different terms in the multi-word, but now we do, and this also increased the coverage. Another thing which was not seen by the previous slides, and that we do now, is that we now compute the Levenshtein distance between definitions before adding them to a scene set. We do this because sometimes different dictionaries have very similar definitions for the same word. And sometimes there's only 1 comma that changes, or 1 character that changes, or 2, but the definition is basically the same. So we avoid adding very similar definitions. So, as I said, this was just a first approach. We have many ideas for future improvements, especially on OnTopET. But on this part of the work, we should probably try different weights to different relations, and not just to hypernymy, as we have done. We should try to find alternative definition sources, and I'm thinking on the World Wide Web, not just Wikipedia, but online dictionaries, I don't know. But the most important thing is to keep on improving OnTopET's reliability, because it's a resource created automatically. It still has a lot of issues, and I believe that this procedure, if it would be applied to a 100%, a virtually 100% reliable resource, it would also provide better results, of course. And that's all. If you want, okay, you now have time for questions, but tomorrow, on Thursday, I have registered for a small demo, so you can meet me at the demo room at 11:30, not at 10:30, because it might be too early after.
Thank you. Questions, please?
Everything is clear. No one has questions.
I have a question.
Okay.
I have a question. Can you show us the slide number 8, please?
Here are what's happening? I don't know what's happening. This is going back. 8. This one. Yeah.
Can you explain with more detail that expression WSI?
Oh, this is just the score of the scene set and the definition. So SI is a scene set and DJ is a definition. And sorry, SI is a scene set and DJ is a definition. And basically, I'm just saying that this score should consider the intersection between the contexts. So you can use any similarity measure if you want, but yes. But as I shown in the slides after this, I just used the number of common terms.
Okay.
And then a boost for hypernyms.
The number of common terms. Did you consider the multi-word expressions? No. For this case.
So in the work, when I wrote the paper, a multi-word expression was a multi-word expression. So you would have to find exactly that word in the definition, which occurred not very often. But now I just split the multi-word into atoms, and it's easier to have intersections. Yes, it's completely true. Yes, we have also that drawback.
Okay, thank you. No questions, please?
Are you planning some sort of source routing to make some page that makes it possible for all the world to help in validation the glosses
the resource? Yes, that would be nice. If anyone would have the time to develop such a website or such a tool, I would be glad. But it's not one of our priorities. We are thinking in the near future. That's something we have been thinking for some time, but let's see if we can do it in the near future, to add confidence information to the resource, and when I say to the resource, it means confidence of the words in the scene set, confidence of the connection of scene sets by semantic relations, and also confidence on the assignment of the definitions to the scene sets. But that's something that will probably come in the near future.
That would be very useful,
yes.
Of course.
I know.
More questions? Thank you.